All right, so in this video, I want to introduce hypothesis testing. Specifically, I want to get comfortable with the language of hypothesis testing. There's a lot to hypothesis testing. Hypothesis testing is probably the single most important topic for the rest of the class. We'll see it over and over again, and your ability to kind of understand hypothesis testing will have a large effect on your grade for the rest of the class. So it's definitely one to spend a little bit of extra time on, which is why I want to make this video just talking about the language, the symbols, all the different ideas that we'll be doing, and then actually work completely through a few examples in subsequent videos. So anyways, here's an example. It's a very typical hypothesis testing example. There's something that we want to study. In this case, it's vitamin C, and whether kids who take vitamin C get sick less often. And we make these assumptions. We say that we somehow know that the average number of times a kid gets sick per year is 2.5. So this right here is a population average, has nothing to do with vitamin C. This is all kids here. And a standard deviation of 0.9. So we have these population parameters here that are given to us in the problem. And then we get a random sample. And this random sample of 100 kids who take vitamin C, so that 100 will end up being important also. I guess I can put a box around it since apparently that's what I'm doing with important numbers. And we give it to them daily for a year, and we calculate how many times these kids get sick, and we get this 2.3. So if you're paying attention to these numbers, you might notice that 2.3 is less than 2.5. Right, 2.5 presumably is the number of times that a kid gets sick in the population. But in this sample of 100 kids who's taken vitamin C, they only get sick 2.3 times. You're like, 2.3 is less than 2.5. Right, so therefore vitamin C must work? Well, no, not necessarily. Right, the problem here is this 2.3 is not the population of all kids taking vitamin C. It's just the sample of kids taking vitamin C. If I knew the population average of kids taking vitamin C, and that were less than 2.5, well then yeah, vitamin C works. But because this is just a sample average, there's some variance associated with it. Right? The idea is maybe just out of dumb luck, these 100 kids who I gave vitamin C to weren't going to get sick that many times. Maybe the vitamin C doesn't have anything to do with it. So what we do with hypothesis testing is we have to decide, is this 2.3 enough less than 2.5, informally speaking, that we can attribute the difference between the 2.3 and the 2.5 to the fact that this 2.3 comes from kids taking vitamin C. And if it is, well, then we can say that vitamin C decreases the frequency of kids' sicknesses. And if it's not, well, then we can't say that. We don't know if vitamin C decreases the frequency of kids' sicknesses. So that's kind of what we'll be doing with hypothesis testing. I think the biggest challenge with hypothesis testing is there's so many different ideas and symbols and language of it floating around. So maybe I can start with averages. There are 3 notions of average in a hypothesis testing question. The first one is this 2.5 here, kind of my baseline population average. The thing that I'm studying, vitamin C in this case, might get some results on it, but they're meaningless unless I have some sort of baseline number to compare it against. You can kind of think about this as like the control group and this the treatment group. Although this doesn't deal with a sample, this deals with the population. This baseline population average is one of the notions of averages that I have in these problems. And then I have my control sample average. And maybe I should even note in this problem, this is the 2.5 and this is the 2.3. And you're like, those are the only 2. Why'd you say that there are 3 notions of average? Well, there's a third one that's not told to us in these problems, and it's the control population average. And the problem is that thing's unknown. It's always going to be unknown in these problems. Because if I knew the control population average, if I knew that the population average, if everyone in the population took vitamin C, if I knew how often they'd get sick, all I'd have to do is see if that number is less than this 2.5. And if it were, I'd be good. I say vitamin C works. But I'll never know the control population average, unfortunately. So hypothesis testing is not that easy. But there still is a path. There's still a way we can do this because we know the control sample average. We can make inferences about the population average, right? That's what we've been doing. That's what we did with confidence intervals. You knew a sample average, and you made guesses at the population average, the population that sample corresponds with. So informally, we're going to take this 2.3, and we'll make inferences about the control population average. And then based on what we conclude this to be, we'll see if we're confident that it's less than 2.5. So we have these three different notions of averages in these problems. Since we have these three different notions, we're going to need some symbols. Some of the symbols will be consistent with what we've been doing in this class. For example, my sample average, we've been using the symbol x bar for that. And that's what we'll do in this case. In this problem, you want to be able to read this and tell that x bar is equal to 2.3. And then the sample average and then the population average, you're probably thinking we should use mu for that, right? Mu should be the 2.5. We're actually not going to use mu for this. And the reason we're not going to use mu for this is we're saving the symbol mu for down here in part 3. This unknown population average, the thing that we want to use x bar to make inferences about, is what we're going to call mu. So mu is unknown. And you're like, all right, well, if you're using up mu here for this third notion of average, what symbol are you going to use for this first one? What symbol is 2.5 going to be? It should be mu, or at least something like mu, because it's a population average. But we don't want it to be exactly mu, or it'll be really confusing. We'll have two different mu's in the same problem. So what we do is it's a mu with a little 0 in the subscript. The way you say that is mu naught. Mu naught, like British 0, N-A-U-G-H-T. And these are our three different notions of average that you'll see will pop up in all of these problems. In every single 4.3 hypothesis testing question, you will always be told mu naught and x bar, and you will never be told mu, but you'll want to understand what the symbol mu means, because the language of this, as we go through the different steps, you'll see mu popping up a bunch. And you'll want to understand what it means. If you can get comfortable with these three notions of averages that show up in these hypothesis testing problems, it'll make these a lot easier for you. So going through this problem, we already recognize that this 2.3 is x bar and this 2.5 is mu naught. You can label those if you want. We also have a sample size. We've been using the symbol n for that. We still will. So n is 100 in this problem. And then we have a standard deviation. And if you read this really carefully, this standard deviation corresponds with the population. Right? It goes along with this 2.5. So we're going to use the symbol sigma for that. Sigma is 0.9. Can I conclude with 95% certainty that taking vitamin C decreases the frequency of kids' sicknesses? A couple things here. We'll always be told the level of certainty that we're using in our problem. And it's going to turn out that it's more useful for you to know that this means that alpha is 5% than it is to write down that we have 95% certainty. So again, alpha is always 1 minus your level of certainty. So 95% certainty means alpha is 5%. So just like we saw with confidence intervals, but now it'll end up being more important in the process, so you might want to write it down right at the start. It also turns out that there's three different types, three different flavors of these tests. This word decreases will be really important. When you're doing these tests, you'll have a claim that you're making, and that claim, informally speaking, will either be that something increases something else, something decreases something else, or something affects something else. We don't specify the direction. And those three types will look a little bit different. And in the next example, we'll get cases of each of those three types. But for now, I just want to make note of this word decreases. It's really important. When you start doing these problems, it'll benefit you to read through the problems and label all the information that's given to you. So I guess I should do that. This 2.5 is the mu naught. And this 2.3 is x bar. Sure. You don't have to make note of these three notions of average every time you do these problems, but it's good to be able to think about these, especially the first time through. So when you read through this problem, I recommend doing all this, but it won't be required. The first required step in our class, it's going to be a 4-step process, will be to state the null and alternative hypotheses. Like I said, there's a lot of new vocabulary in this section. Null and alternative hypotheses are two words you haven't heard yet in this class. You're going to end up stating these things symbolically, and I'll teach you these symbols and I'll write them in blue. Kind of what will be required in these problems will end up being written in blue. But before I get to that point, I want to talk about them more informally, get you to understand what you're writing when you end up writing these in symbols. So for color coding purposes, red will be the stuff that I kind of want you to learn and that I kind of recommend up here writing down. But blue is what will be kind of the required part, which will be graded upon. So the null hypothesis. Actually, maybe we'll start with the alternative hypothesis. The alternative hypothesis is always the claim that's being made. All right, so in each one of these hypothesis testing questions, there'll be some claim that's being made. In this case, the claim is that taking vitamin C decreases the frequency of kids' sicknesses. So in this case, maybe shorthand here, vitamin C decreases sicknesses for kids, I guess. The claim is always the alternative hypothesis. So it might be easier to start with the alternative hypothesis. The null hypothesis is a little bit harder to understand. The best thing I've heard, the best description of what the null hypothesis is it's the skeptical point of view. Maybe I'll write the skeptic's point of view. What do I mean by the skeptic's point of view? Suppose that you're skeptical, right? I come in and I tell you vitamin C decreases kids' sicknesses. If you're skeptical, you're like, no, it doesn't. Right? You're not saying that vitamin C increases kids' sicknesses if you're skeptical. You're just saying, no, I don't think that you're right. I don't think vitamin C does decrease kids' sicknesses. Informally, you might say, vitamin C has no effect on sicknesses. And that's the skeptic's point of view, and I know that that's a little bit vague, but it's sort of the best I can do this first time around. We'll always have an alternative hypothesis and a null hypothesis. The alternative hypothesis will always be the claim. The null hypothesis will always be the skeptic's point of view. So in this case, in English, the alternative hypothesis is that vitamin C decreases sickness for kids. And the null hypothesis is that vitamin C has no effect on sickness for kids. What I want you to write are not these sentences, but something equivalent to these sentences symbolically. And the nice thing is it's a nice shorthand. It'll go really quick for you. The way you write the null hypothesis is with H0 and then a colon. H0 means the null hypothesis, and then the colon means is. And H1 or HA, I'll use H1, some books use HA, it doesn't really matter. That means the alternative hypothesis is. So the null hypothesis is, the way you say that, H not colon. The alternative hypothesis is, the way you say that statistically, is H1 colon. So when I ask you to state the null and alternative hypotheses, you'll always write H not colon and then something, H1 colon and then something. The good news is that H naught and H1, when we're in 4.3, will always compare together the two things, the same two things. Two different notions of averages. The two different notions of averages that it's going to compare together are 1 and 3 up here. It's always 100% of the time going to compare mu and mu naught when you're in 4.3. Mu, I can't write any numbers because mu is unknown, so I'm just going to write the symbol mu here. It's going to end up showing up for the null and the alternative hypotheses. And I'm going to compare that to mu naught, although the standard is not to write the symbol mu naught, but instead to write what it's equal to, 2.5, because again, mu naught will always be given to in these problems. So I want to compare mu and mu naught. Note I'm leaving a little bit of room in there because I have to write a symbol in between them. Both the null and the alternative hypotheses in 4.3 will always compare together mu and whatever number is given to you for mu naught. And you're going to put a symbol in between. What do you mean a symbol? A symbol like a mathematical symbol. Think equal signs, less than signs, greater than signs, that sort of idea. So what goes in there? Well, the null hypothesis, the skeptic's point of view, is that vitamin C has no effect on sickness. If vitamin C has no effect on sickness, then the population average number of sicknesses, 2.5, will be the same as the population average number of sicknesses for my control group. This hypothetical idea, if everyone in the population took vitamin C, the skeptic is saying that if everyone in the population took vitamin C, they'd still have 2.5 sicknesses per year because vitamin C has no effect on sicknesses. The null hypothesis, the skeptic's point of view, is that mu equals mu naught. Good news, this isn't specific to this problem. every single hypothesis testing question in 4.3, the null hypothesis will be mu equals mu naught. And mu naught will be a number given to you in the problem. Really, the only thing that changes is the symbol that you put down here for your alternative hypothesis. There's 3 different options. Maybe this is in red or something. 3 options for this symbol. And they are a greater than sign, a less than sign, or a does not equal sign. And the good news is, if you wrote these all in the right order and you're following through these steps, trying not to trick you, since this is an intro to statistics class, I'm going to use language to make this pretty straightforward what symbol you use. What am I talking about? Okay, first, just from an understanding point of view, the alternative hypothesis is the claim that's being made. So in this case, the claim is that vitamin C decreases sicknesses. If vitamin C decreases sicknesses, then this unknown parameter mu here would be less than 2.5. Right? I don't know what it is, but if vitamin C decreases sicknesses, then if everyone in the population took vitamin C, I'd expect the population average number of sicknesses to be less than 2.5. Right? In this case, the symbol that I'm going to put in here is a less than sign. If you were reading this problem and this were like the midterm or something, the way you could figure that out is when you're reading the problem, this word decreases. I claim that vitamin C decreases the frequency of kids' sicknesses. That's the clue that you put a less than sign right here. If the claim were that vitamin C increases the number of sicknesses, you put a greater than sign. Put this first option. If the claim was vitamin C affects the number of sicknesses that kids have. So the claim isn't saying that it's necessarily greater or it's necessarily less than this 2.5, just it's different than. And we put a does not equal sign in here. And I'll do examples of all 3 when I work through an actual example, but the purposes of this one is just to get the vocabulary down. So as far as vocabulary goes, these are your null and alternative hypotheses. What's inside this box is what you would be graded upon. It's worth pointing out that anytime you put a less than symbol here, it means you have what's called a left-tailed test. You don't have to write that it's a left-tailed test, but I typically do. You'll see for future steps, it's useful to have written down that's a left-tailed test. Had you put down a greater than sign here, it would have been what's called a right-tailed test. And if you put down a does not equal sign, it's what's called a two-tailed test. And again, we'll see examples of those in future videos. But in this case, since the claim was that it decreases sickness, it's a less than sign here. And anytime it's a less than sign, it's a left-tailed test. Those are your null and alternative hypotheses. The next step, anytime I ask you to do hypothesis testing, well, eventually you're going to be drawing a picture. But it won't be till step 3 you're drawing a picture. If you're drawing a picture, you better give the reader some context for your picture. I'm going to always ask you to state and justify the shape of the distribution, then tell me the center and the spread. The good news is these are going to be pretty consistent. Right? The shape of the distribution probably won't surprise you, just like it's been everywhere else in this class. It's going to be approximately normal. You might be like, wait, how do I know it's approximately normal? It doesn't say anywhere up here that the number of times that a kid gets sick per year is approximately normal. It's probably not, right? You probably get some kids that are getting sick a whole bunch. Maybe it's right-skewed. I don't know. It doesn't say. So how can you assume that it is? Well, what I'm going to be drawing when I draw my picture down here is the sampling distribution. So the shape of the parent distribution, the shape of one kid's sicknesses isn't even relevant. The central limit theorem tells me that as long as n is greater than or equal to 30, the sampling distribution is approximately normal. So I'm good. The shape of the sampling distribution that I'm about to draw is approximately normal because n is greater than or equal to 30. That's a consequence of the central limit theorem. What about the center of the distribution? Okay, first the short answer. Like, we have 3 different notions of average. How am I ever going to know which one to use for the center? It's mu naught. If you want to just say the center is mu naught, in this case it's 2.5, we're good. There's technically a little bit more to it than that, but as far as your grade, you write this, we're 100% correct. If you're wondering what's a little bit different, really it's not mu naught that is the center, it's mu that is the center. And you're like, how can mu be the center? Mu is unknown. True, but the logic of hypothesis testing is you assume the null hypothesis is true. So I go in there assuming that vitamin C doesn't work at all, in which case mu equals mu naught. So really what I should say is the center is mu, but I'm assuming the null hypothesis is correct. And if the null hypothesis is correct, then mu equals mu naught, and mu naught was equal to 2.5 in this problem. But I don't really want you to write that, right? That's going to be super confusing and nobody will know what to do. The number you're going to put in the center of your distribution is the number that's given to you as mu naught in the problem. The center, mu naught, is 2.5. The spread, it's a sampling distribution, so it probably doesn't surprise you that it's not just sigma and is instead sigma divided by the square root of n. So in this case, sigma was what? 0.9 and n was 100. So I just do 0.9 divided by the square root of 100. And as we've been doing, you don't have to calculate this if you don't want. If you felt like it, you could throw that into a calculator and you get this number. Sometimes it works out really nice like this case. Sometimes it doesn't, in which case you probably just want to leave your answer exact like this. Shape, center, spread. That's the second step. Third step, probably most important step, is to draw the picture. There's a lot to drawing the picture. There's two different options. Different options. And I'm not even going to get into that in this video. I'm going to take a whole nother video to explain these two different options. But there's a way that you're going to draw a picture with all of this information up here from step 2 that will help you in step 4 draw your conclusion or make your conclusion. I want to talk a little bit about the conclusion, even though we're not going to draw the picture in this example, because I think that'll be instructive as far as the language of hypothesis testing, what you're actually doing. So again, more to drawing the picture. There's two different options. One is called the classical method, and that's got its own picture. And one is called the p-value method, and that's got its own picture. And you'll be told which of these two methods to use, and I'll explain the advantages and disadvantages to each of the two methods. That's all for a different video. Just know that there is a picture you draw, and when you draw that picture, you'll be able to make your conclusion. So it might be kind of weird that I'm talking about the conclusion now, even though we're not drawing the picture, but I'm not going to talk about it too formally. I just want to talk about informally what's going on here. When you're making your conclusion, there's two different options. Two different possibilities, maybe, not options. So whether you're using the classical method or the p-value method, it doesn't matter. There's two different possibilities for what your conclusion can be. In other words, there's only two different things that can come out of your hypothesis test. Either you say that the claim is true, or, and you're like, let me stop you here, the claim is false? No, that's not it. Either you say the claim is true, or you say there's not enough information to say that the claim is true. Whoa, that's really strange. That doesn't seem symmetric, right? I'd think it would be the claim is true or the claim is false. But that's not what you do. The reason why is because we're going to start out by assuming the null hypothesis is true. And we're going to draw this picture in step 3, assuming the null hypothesis is true. And then we're going to look at our picture and see if we got a really strange result. And if we got a really strange result, we're going to go back here and be like, we must have been wrong to assume the null hypothesis is true. So technically what we'll say is we reject the null hypothesis. We start out by saying the null is true. If we get a strange result, we reject the null hypothesis. So strange results, and that maybe gets quotation marks. That means we're going to reject the null hypothesis. Wait, what just happened there? Okay, we're assuming the null hypothesis is true. If the null hypothesis is true, we'll be able to draw this picture in step 3, it'll turn out. And when you look at this picture, you'll be able to tell if something really strange just happened with your sample only getting sick 2.3 times per year. And if something really strange just happened, you'll go back and be like, I must have been wrong to assume the null hypothesis was true. So I'm going to go and change that assumption to rejecting the null hypothesis. If you reject the null hypothesis, if you say that this is gone, if the skeptic is wrong, then all you're left with is your alternative hypothesis. You say that your claim is true. Alternatively, if result isn't strange, well, if we don't get a strange result, if we assume the null hypothesis is true and we don't get a strange result, then we can't reject the null hypothesis. So what does that mean? You might think that it means the null hypothesis is true and therefore the claim is false, but it doesn't. If we cannot reject the null hypothesis, then we can't say that the claim is true. Which logically is different than saying that this claim is false. Think shrug. Think, I don't know. I don't know what's going on here. I don't know if vitamin C decreases the frequency that kids get sick or not. I have no idea. I'm just kind of shrugging my shoulders and saying I need more information. There's only two possible conclusions that you can make. One will correspond with this first guy, one will correspond with this second guy. But really, I can't give you the fine details of this just yet because I have to show you how to draw the picture. But drawing the picture is intense enough that it deserves its own video. So what I'm going to do is I'm going to pick up with this same example in the next video. In this video, I just want you comfortable with the notation and the symbols, the three different notions of averages, the null and alternative hypothesis, and then maybe big picture what we're doing when we're making our conclusion.